Hello dear students, this is Dr. Aisha Nazuk here. Welcome back to my channel Rao Hub, and today we are going to cover the topic of hypergeometric distribution. If you want to efficiently use these lecture notes, so it's highly advisable that you refer to chapter 6 of a book which is authored by Douglas Lind and other authors. You can see the title of the book here on the screen. The good part about this book is that the answer to the exercises are also given at the end of the book. And if you are interested in how to download this book, you can easily watch my video about how to download books from the Genesis library. This video is also available on the Rao Hub. And if you want me to post the link to this video, you can post a comment in the comment section and I'll post the link. Okay. So without further ado, let's focus on the contents of today's lecture. As I said, this is about hypergeometric distribution. This is one of the discrete probability distributions. If you are watching this video for the first time, in fact if you are exploring the concept of probability for the first time, then it's highly advisable that you should refer back to the earlier videos on probability. Anyhow, today we are talking about hypergeometric distribution. So let's set the basic or the assumptions of the hypergeometric distribution. The hypergeometric distribution is suitable for the scenarios where we have dichotomous or binary outcomes. For example, without any disregard to different or diverse type of gender, let's focus that in a particular race or a marathon, only the male and female are participating. So just for the purpose of clarity, if you focus on this figure, or the diagram, you can see that 2 females are participating in this marathon, while we have 1, 2, 3 and 4 males. So total we have 6 persons, out of which 2 are females and 4 are males. So hypergeometric distribution is relevant for binary outcomes. Now, all the experiments having binary outcomes are not hypergeometric. There are certain other assumptions. So this is just the first assumption of hypergeometric distribution, that the outcomes are binary. Next, how are we going to further set the basics for the other assumptions? First of all, let me discuss a scenario. For example, if in this marathon, let's say if a female wins in the first marathon, then she is given a complimentary coffee or a tea voucher for a cafe. Then a second marathon is arranged and same offer is offered or given for a female winner. Now we have different type of offer for males as well, but for currently the point of the discussion here is what I'll do in the next few slides. Just a minute. If you look at let's say in the first marathon, this lady which I have encircled using this yellow circle part, let's say this female wins the marathon and then she is not participating in the second marathon, right? So what happened? For example, if I diagrammatically display it, I have put on some some segment of the diagram here intentionally to hide that lady, to allude toward the fact that the lady who won in the first marathon is no longer participating. So if we want to predict the likelihood that female wins in both marathon, right? So if we want to predict this probability, first of all what we need to focus is that the probability of female in the first marathon is 2 by 6. How? If you look back at the original image, you can see that we have 2 females and the total is 6. So the probability that any female wins in this or the first marathon, that probability is 2 by 6. Now the probability of female in the second marathon, pardon that this is a typo, I should have written second. So probability of female in second marathon, this is, now we are left with only 1 female. So the probability of a female winning in the second marathon is equal to 1 by 5. So why am I comparing the probability of female winning in first and the second marathon is because I want to emphasize on the fact that the probability of success in hypergeometric distribution, it changes from trial to trial. And what is meant by success? the category which you want to analyze. For example, here I want to predict the likelihood of a female winning the 2 marathons. So the probability of success means probability that a female wins. So you can see that the probability of success or probability that a female wins the marathon, it changes from trial to trial. In the first trial it was 2 by 6. You can see 2 females out of 6. In the second trial, when the first lady who won the marathon, we set her aside and then the marathon is again organized. Now we are left with only 1 female, so the probability of female is 1 by 5. So the second assumption of hypergeometric distribution is that the probability of success changes from trial to trial. Now, a highly relevant or interlinked assumption of hypergeometric distribution is that the successive trials are not independent. Now what does that mean? You see that what happens in the first marathon or in the figure 1, for example, if this is figure 1, so whatever the outcome of figure 1 or the first marathon, it determines that what will be the list of participants in the second marathon. For example, if this lady wins, then she will be set aside for before the second marathon. But for example, if let's say this lady here in the third position, counting from here, so if she wins, then she will be set aside, right? So the second figure or the second marathon is dependent upon the first marathon, right? So this is what it is written here. It matters who won in the first marathon. So suppose if a male wins in the first marathon, then the second figure may look like this, right? We are discarding a 1 male, right? So successive trials are not independent, right? So this is the third assumption of hypergeometric distribution. So now I have properly enlisted the assumptions here that the outcomes are 2 mutually exclusive categories, success or a failure. For example, in the example of marathon, the 2 mutually exclusive categories were gender, male and female. Once again, without any disregard to diverse types of gender, only in this example I have considered male and female. Second is that the probability of success and failure changes from trial to trial. I have already discussed, for example, probability of success, that is probability of a female, will change from marathon to marathon. Similarly, probability of a male will also change from marathon to marathon. So that is why success, that is in our example probability of female, and failure, which is in our example probability that a male is selected, it changes from trial to trial. And then the third one was interlink. As I said, that different marathons, the composition of participant is linked with what happened in the previous marathon. So the trials are not independent. So these are the 3 assumptions under which hypergeometric distribution is applicable. Now one interesting point is that if population is very large, then we can use binomial distribution instead of hyper. In other words, let me focus on a point here, then I'll come back to these slides. For example, if in the example of marathon, if there are 1000 participants in the race and out of which 300 are females and 700 are males, then the probability of female at the time of first marathon is equal to 300 divided by 1000. Now assuming that whosoever female won the first marathon, she is set aside and the marathon is again organized, so then we are left with 299 females and 700 males. So the probability of female will be 299 divided by, this is a typo, it shouldn't be 1000. So 299 divided by 999. Why 999? Because total participants are at the time of second marathon, they are 999, because whosoever won the first marathon, she is set aside. And then we are left with 299 females. So the probability of female at the time of second marathon is 299 divided by 999. Pardon, it's a typo, it's not 1000, okay? So you can see that if population is very large, like we have 1000 participants, it's a large population. So 300 divided by 1000 or 299 divided by 999, these will be almost the same. So this is the reason, if the population is very large, we can say that the hypergeometric distribution converges to binomial distribution. So let's empirically calculate the probability. Let's say we organized 100 marathons, and we want to see that out of these 100 marathon, in 2 of the marathons female is a winner. So now why am I applying the formula for binomial distribution? Is because this is a large population. We have, as I said, 1000 participants. So I can fairly, you can say, approximate the probability using binomial distribution. As I said, in larger population, whether you are doing sampling with replacement or without replacement, it doesn't make much of a difference. As you can see that if we have 1000 participants, then the probability of female from trial 1 to trial 2, it remains almost the same. I mean, not exactly same, but similar. So what we will do, we will use this probability of female at the time of first trial. It's equal to 0.3. So I'm going to use it as an approximation, that I'm assuming that the probability of selection of female is 0.3 throughout the sequence of 100 marathons. And when can I make this assumption? When the population is very large. So you know that the formula for binomial distribution is total slots combination you are picking. So we have 1000 total slots, out of which we want to fill 2 slots with female, that is in 2 marathons female is winning. So probability of a female winner raised to the power 2, whereas the total is 100, so the remaining 98 are won by a male. So if the probability of a female winning is 0.3, then it's understood that the probability of male winning is 0.7. As I said, that there are only 2 categories, in both in binomial distribution as well as in hypergeometric distribution. So rest of the things are just combination. So you can, by the way, if you don't know about the concept of permutation and combination, by the way, it's high time that you refer back to the earlier videos before you gain your grip on the concept discussed in today's video. So this is, you can see, a probability which is a very small number. So out of a sequence of 100 marathon, this is the probability that 2 times a female wins the marathon. And by the way, when can we apply the approximation of binomial distribution into hypergeometric? As a rule of thumb, whenever the sample size divided by the population size, right? Whatever is the sample size, for example, here the sample size is 100, a sequence of 100 marathons. So what is capital N population size? For example, here we have 1000 participants. So in this example, lowercase n or small n is 100, capital N is 1000. So whenever this fraction is greater than or equal to 0.05, then we can use this method of approximation of probabilities using binomial distribution, right? Okay, so before I proceed further, so now we have discussed the assumptions of the hypergeometric distribution and under which scenarios we can keep on using the binomial distribution instead of using hyper. Now is a high time that I tell you what is the exact formula of hypergeometric distribution. So before moving to that formula, let's focus on a empirical or a numerical question that will help you set the foundation for the formula. So let's say the question is, in how many ways can we select one blue ball if we draw 4 balls one by one without replacement from a bag containing 5 blue and 6 red balls? So you can see that the sample size is 4 and the population size is 5 plus 6, 11, right? So capital N is 11 and small n is 4. You can easily calculate that the fraction small n divided by capital N, this will not be greater than or equal to 0.05. So I cannot apply the binomial approximation. I will simply apply the formula for hypergeometric. Okay, so what's the formula? You see, we have to select one blue ball, right? And the total balls that we are drawing are 4. So out of these 4, one should be blue. So this is one possibility that the third red ball is drawn, or the fourth one, or the sixth one, because you see how many reds are there? 6 reds. So maybe, for example, if I label these ball as R1, R2, R3, so on. So R3 means that the third red ball is drawn, R4 means that the fourth red ball is drawn, and so on. So this is one possibility, but we are not interested in the order of the ball. For example, which ball, if this is red 3 is here, even if we have, for example, R2, that is the second red here, we are treating all those possibilities as same. So we know that we apply the formula for combination whenever the order is not important. So how many red balls in total are there? We have 6 red balls and 5 blue balls. We want to select one blue ball. So 63 ways to sample 3 red balls out of 6, right? Total we have 6 red balls. And why we are drawing 3 red balls? Because if we have one blue and we have to complete the sample of size 4, then it's understood that the remaining 3 should be red. You see, the sample size is 4, and out of these 4, 1 is blue. So 5C1. And why 5C1? There are in total 5 blue balls. So 5C1 means all possible ways in which I can select one blue ball out of total 5 blue balls. Similarly, 6C3 ways to sample 3 red balls out of 6. Once again, why am I drawing 3 where in the question it isn't written directly, but it's understood that if the total sample size is 4, 1 is blue, then it's understood that the remaining 3 are red, because we have only 2 categories, blue and red. So selection of 3 red balls can be done in 6C3 ways, and 1 blue ball can be done in 5C1 ways. Now we are going to multiply these two numbers, whatever the resultant number of these combination is. Why am I multiplying? Because both these conditions are mandatory. It's not optional. It's mandatory that we are drawing 3 red balls and 1 blue ball. So whenever the conditions in an experiment are mandatory, we multiply them. So 6C3 multiplied by 5C1 divided by 11C4. So how come this 11C4, by the way? So you see, in total we have 5 plus 6, 11 balls, and in the total sample size is 4. So actually I am dividing by all possible ways in which a sample of size 4 could be selected out of a total of 11 balls. Why? Because probability of an event is number of ways that event can be performed divided by number of points in the sample space. So what's the sample space? All possible ways of selecting 4 balls out of these 11 balls. So that's why I'm dividing by 11C4. So now you can see if my category of interest was blue ball and the category not of interest was red ball. In general, what I can say, S is my category of interest and N minus S, capital N minus S is my category not of interest. For example, in the previous example, what is S? If I am selecting one blue ball, so S is category of blue balls. So how many blue balls are there? 5. So S will be 5. What is capital N? Total balls, which is 5 plus 6 equal to 11. You can see N is the size of the population, S is the number of success, X is the number of success in the sample. For example, here we were analyzing the probability for one blue ball, so X was 1. So this is the general formula, SCX N minus S Cn minus X divided by capital NCN. By the way, just don't get confused by these notations. This simply means that we are applying 3 combinations here: total population, combination, sample size. Then category of interest, combination, how many observation you want from the category of interest. Then category not of interest, see how many balls or how many observation you want from category not of interest. So this is the general formula for hypergeometric distribution, and this is one possible numerical example of that formula. So Let's do another example. Let's say Playtime company employs 50 people in the assembly department. 40 of the employees belong to a union and 10 do not. Now what we are doing, the total population is 50 and the two categories are either belonging to the union or not belonging to the union. So 5 employees are selected at random to form a committee. What is the probability that 4 of the 5 selected for the committee belong to a union? So what is the category of interest? Belonging to the union. So how many are belonging to the union in the population? 40 belongs to the union. So 40 is the category of interest and the remaining 10 do not belong to the union. So that is my category not of interest. And I want 4 of the 5 selected to belong from the union. So you can see capital N is 50. Why is it 50? We have total 50 employees. S is 40. Why is S or the category of interest 40? Because we are interested in belonging to the union. So category of interest is belonging to the union, which is 40. X is 4. Why is X 4? Because you can see that we are computing the probability that 4 of the 5 selected belong to the union. So X is 4. N is 5, that is sample size is 5. Why is it 5? Because we are selecting 5 employees. Okay, so now the required probability is out of 40, that is out of those who belong to the union, we select 4. So 40C 4 ways to sample 4 out of a total of 40. So these are all possible ways in which 4 employees who belong to the union can be selected out of a total of 40 employees. So in the population you see we have 40 that belong to the union and we are analyzing in how many ways can we sample 4 out of these 40. So 40C 4 multiply by 10C, or you can say 50 minus 40, which is 10. So 10C 5 minus 4. Why is it 5 minus 4? The total sample size is 5. 4 of them belong to the union, so it is understood that the remaining ones will be not from the union. So this will be 10C1. So why 10C1? You can see that in the population there are 10 employees that do not belong to the union and we are sampling one of them. So 10C1 ways to select one employee out of those 10 that do not belong to the union and divided by 50C5. So why 50C5? Total population is 50 and the sample size is 5. So you can see that if I add, let me go to the math type for a moment. So here I was saying that we have 40 C4 right, multiply by 10 C1 divided by 50 C4. So you can see just a minute, yeah. So we have 40C4 ways to sample 4 those belong to the union, 10C1 ways to select those who do not belong to the union, and here we have 50C5. Why is it 50C5? As we said, we have total 50 employees, we are sampling 5 employees. So you can see that the sum of these two, 40 plus 10, 50, it is a mandatory condition. If you have enlisted all the entries correctly, then this upper indices 40 and 10, that should add to the upper index here, which is 50. Similarly 4 plus 1, it should be 5. Why? Because the numerator is just a split of the denominator. In the denominator I am not partitioning the sample, whereas in numerator I am partitioning the same sample of 5 individuals into two types. 4 belong to the union, 1 doesn't belong. So this is necessary that if you add the upper index in the numerator, it's equal to the upper index in the denominator, and similarly the lower index sum is equal to this value 5. Okay, so this was a numerical example of hypergeometric distribution, and I've already told you that I've already discussed this, that if the sampling is with replacement or without replacement, but if the population is very large, then it doesn't matter whether we are doing sampling with replacement or without replacement. So as a rule of thumb, whenever the sample size divided by the population size is greater than or equal to 0.05, then we can approximate the probability by using the binomial distribution as well. I mean, it's not mandatory that you use this approximation, but the legitimacy of this approximation, if you want to use it, is that small n divided by capital N should be greater than or equal to 0.05. So this was about hypergeometric distribution. And by the way, just on a lighter note, I thought it's good that I connect with my audience as well, because it's often said that a good teacher is one who induces the sense of belongingness and connectivity with the students. So whosoever my viewer in the international cyberspace, I so want to connect with my students. By the way, those of you who have watched the video for the first time, I'm a professor in a university in Pakistan, which is NUST, National University of Science and Technology. And my students, I always try to connect with my students. I do interactive activities. I never classify my students as backbenchers or sometimes categorically mentioned by some teachers, good student, bad student. So in my class there are no good or bad students. All of you have your unique learning experiences and learning curve. So here, by showing a shot that I captured myself yesterday when I was hiking on Buddha caves in Islamabad. So this is my humble effort to trying to connect with my audience. So thank you for watching. This is the email address. You can always drop me an email if you want me to send these lecture slides, and you are more than welcome to explore other videos on this channel. There are diverse types of playlists available. So thank you once again for watching the lecture content.